Hello, everyone. Welcome to pre-lecture 25. This lecture is going to focus primarily on the second law of thermodynamics, getting into some Gibbs free energy as well. Okay, so last class we talked about the third law of thermodynamics that states that the entropy of a perfect crystal at absolute zero will have an entropy of zero as well. And that would be ultimately because once we have a perfect crystal at 0 degrees Kelvin, we only have one microstate. So if we were to plug that into the Boltzmann equation, we would of course get an entropy of zero. But in reality, of course, we have many, many microstates within much more than a perfect crystal within the universe and really all chemical systems. So we also ended last class with just a brief preview of how to calculate absolute and standard entropies. And so entropies can be calculated by making calorimetric measurements. So you may remember that term from General Chemistry 1 when we talked about thermochemistry and making measurements with regards to enthalpy. So entropy could be measured using similar experiments under standard or not necessarily standard, but specific conditions. And that brings us to standard enthalpies. So these are tabulated values per mole of a particular substance, and typically we report them as under standard conditions, which is a pressure of 1 bar and a temperature of 0 degree, or pardon me, 25 degrees Celsius, which is of course 298.15 Kelvin. Okay? And within this, the standard entropy change, so delta S naught, we could call it, is a value that can be computed for any sort of chemical reaction. And so you would use this equation where the standard entropy change is just the sum of all of the entropies of the products subtracted from the sum of all the standard enthalpies of the reactants. And so new here, or this V term, is the stoichiometric coefficient. So in a balanced chemical reaction, any stoichiometric coefficient that is not a 1 would of course need to be multiplied by whatever the standard enthalpy is for a particular chemical substance. And that value can be found in one of the appendices, I believe Appendix G in your textbook. Okay, and so feel free to check those values out. Also, those are not values you would need to memorize. If you would need them, they would be provided for you on an exam. Okay. Great. So that brings us to the second law of thermodynamics. So going backwards, and the second law essentially asks, is there a way to predict if a chemical reaction will be spontaneous? And of course, this is a bit of a leading question coming from me because the answer is yes. And it ultimately derives from the second law of thermodynamics. And that states that all spontaneous changes cause an increase in the entropy of the universe, meaning that we have a more equal distribution of energy throughout the universe because when something is spontaneous, right? And so in mathematical terms, we could measure it with a very simple equation that says the change in the entropy of the universe must be greater than 0 when we have the change in the entropy of the system plus the change in the entropy of the surroundings. Again, in order for something to be spontaneous, that value has to be greater than 0. Okay. So let's think about an actual example here. Say we had liquid water, maybe it was in an ice tray. So if we left that ice tray out on the counter, we wouldn't expect it to spontaneously freeze, right? But if we were to put it in the freezer, we would expect our liquid water to turn into ice, right? So take a moment to consider in this sort of example where we put a tray of liquid water into the freezer and it freezes, what is our system? You should also think about what are our surroundings? And then how can we rationalize that the system's entropy, so uh, we know that our system's entropy must decrease in order for this to happen spontaneously. And so how does that decrease in entropy occur on a spontaneous process? And so take a moment to think about that. If you want to pause the video, you can. But I will go through the answers now. So our system, in this case, would be the water that's within the ice tray, and our surroundings would be the freezer. That freezer is ultimately connected to some sort of electrical outlet that puts electricity into the freezer to move heat out of the freezer outside of the refrigerator or the freezer itself. And so in that case, the entropy of the universe increases because within our system, the entropy decreases, but we get a greater increase in the surroundings of entropy as heat is moved out of the liquid water into the surroundings, which would be ultimately out of the freezer and into, say, our kitchen. Okay? So that would be an example of the systems and the surroundings, both leading towards an ultimate increase in the entropy of the universe. Okay. Just a couple of reminders from General Chemistry 1. So tying together what we learned in our thermochemistry unit with thinking about how we'd quantify this change in entropy of the surroundings. We could define the change in the entropy of the surroundings as the heat in the surroundings divided by whatever temperature it's at. And just a reminder again from General Chemistry 1 that whatever the heat of our system is will be the negative heat of our surroundings. So if our system gives off heat, then that would be, say, negative, or I guess in this case, if our surroundings take in, or pardon me. So in this equation here, say that the heat of our system increases, that heat would have to come from our surroundings, right? So it would be losing the same amount there. If we define this in terms of enthalpy, so if the change in heat is at a constant pressure, then the surroundings is equal to the enthalpy of our surroundings, or the negative enthalpy of our surroundings, I should say. So finally, if we put these together, we get an equation that may come in handy where the entropy of our surroundings is equal to the negative change in enthalpy of our surroundings divided by the temperature. Okay, and so that is the equation we've kind of been building towards that can help us identify the actual change in entropy of a system, because we can't really easily measure the number of microstates, but we can measure something like changes in temperatures, changes in heat, which would also be enthalpy in this case, right? Okay, so this ultimately, or just to point out this out here, this equation also ties together entropy and enthalpy. And so we want an easier way to relate those with regards to spontaneity. And so typically we would define this in terms of Gibbs free energy. And so the Gibbs free energy is a measure of essentially the spontaneity of a reaction. And so it combines our enthalpy term, so our delta H, and the entropy of a system, and then it is defined as the Gibbs free energy here. The free energy, if we were to define what this maybe practically means, it is the maximum amount of usable energy, which could also be defined as the work that a reaction can produce. And so anything that is given off as heat, maybe that is not capable of doing work, it would just be given off as thermal kinetic energy, would not be counted in our Gibbs free energy. Okay. And if we're thinking about this in terms of spontaneity, values of Gibbs free energy, delta G, that are negative will be exergonic, meaning that they are spontaneous, and non-spontaneous processes will be endergonic, which would mean they would be non-spontaneous. Okay. Just in terms of how that would influence, or how our enthalpies and entropies would influence the delta G sign, again, if we have a negative enthalpy, which would be an exothermic reaction, that would be favorable to contributing to a negative spontaneity, meaning that it would make it more favorable. And because we have a negative sign here, if we have a positive entropy, that would also contribute to something being favorable, right? So this sort of reaction diagram should look familiar, although we're usually used to seeing something that is enthalpy, so heat generally on our y-axis. We could also define a reaction in terms of its Gibbs free energy. And so again, just like I said last time, if we start with reactants at a higher free energy and they release free energy throughout the course of a reaction, it would be exergonic, meaning that this reaction on the left would be spontaneous, whereas the reaction on the right would be non-spontaneous, meaning that you have to input free energy from somewhere else in order to get this reaction to occur. Also, just a reminder that exergonicity, spontaneity, has nothing to do with the speed of a reaction. So again, anything to do with how fast a reaction goes relates to the kinetics of a reaction. This just determines if something will or will not happen without the input of energy. Okay. So your textbook had this handy table that kind of shows you when reactions will be spontaneous and when they will not be. So any reaction that is exothermic, meaning that we have an enthalpy less than 0 and an entropy greater than 0, any reaction that meets both of those conditions will always be spontaneous at any temperature. With the opposite, where we have a positive enthalpy and a negative entropy, any process would be non-spontaneous at any temperature. Again, that means it can happen. It would just require input of energy from another source, aka the surroundings. And then finally, we have these two yellow boxes. And so say we have a positive enthalpy, but a positive entropy. In that case, at high temperature, so when we have a high temperature, that will make this term bigger, which will make it overall our delta G more negative. So at high temperature, an endothermic reaction can be spontaneous, whereas at low temperatures, when we have a negative entropy, that process can be spontaneous, but at lower temperatures, right? Where we want to minimize this second part then, where if we have negative entropy, then this term ultimately ends up being positive, right? This figure, I think, does a nice job illustrating that as well, where we have free energy on our y-axis and then increasing temperature on our x. So as our temperature goes up and up and up, at a certain point, these lines would cross, and maybe an endothermic reaction where we have to put enthalpy in or put heat in might no longer be spontaneous if our entropy cost gets too big, because that entropy cost is tied directly to temperature, right? Okay, that's all for the pre-lecture for today. Hope that was helpful. If you have any questions, of course, feel free to email. Otherwise, I would be happy to answer questions in class as well. Otherwise, have a good rest of your day. I'll see you soon.